Okay, so this video would be on solving systems of differential equations. So in general, this skill is useful because it allows you to solve systems that are changing over time, and specifically you'll see that represented through having a derivative in some of the equations. And what's interesting is that this skill relies on you knowing how to do change of basis and diagonalization, which are both techniques that are talked about and mentioned in the previous two videos. And again, this all goes into the bigger picture, being able to solve our LC circuits. And with this last part of this whole process, you should be able to solve these circuits now. And we'll go over the techniques to solve it and just some kind of basic things to remember. So before we dive right into differential equations, I'm just going to talk about some kind of side things really quickly. So one thing is, how do you represent a system? So usually when we represent a system, we have a state variable. It's usually denoted by the vector x of t. So the state specifically at time t. And usually x of t just contains values of however many parameters you are measuring, like x1 all the way to xn, for example. So that's the state variable you're going to use, and then when you have the differential equations for it, you'll usually have, like, for example, d x of t is equal to blank to show the change over time, and that will be one of the equations you need to use in order to solve it. Cool. And then another aside that I wanted to mention is just some common Diff Eqs. Specifically, the main one you will need to know for this class, and the main one that will repeatedly come up, is the fact that whenever you have t, f of t is equal to just any constant, let's say alpha, f of t, then this will become f of t is equal to k e alpha t. And this k right here is just the initial condition. So it's basically a constant, but you solve for it by considering the initial condition. Okay, so now let's go into how do you solve a differential system of equations. And I feel like the best way to understand this is just by running through an example together, and along the way I'll describe the main general steps that you're going to use and just how to proceed. So starting off this journey of system of differential equations, you'll usually be, at the beginning, you'll be given the system of differential equations, and the initial condition. Another option is that you may be, instead of given the differential equations already, you may be given a circuit, and then you would need to use KCL and KVL in order to write the appropriate equations and to figure out the differential equations yourselves. But in general, you'll have initial conditions and these equations to start with, and that's where you want to start your calculations at. So specifically, let's say you're given the equations d dt on a t is equal to and d dt x divided by t minus by x2 of t. Yes. So these are the equations we are starting off, and that's kind of our starting point. So the first step you want to do is write equations in matrix vector form. So this is really Similar to when you're learning Gaussian elimination, you just want to represent the system. Just pretend there's no dTs, there's no differentials yet, and you just want to present it in matrix vector form. So how you would do that in this case is you basically will have on one side, it would be dt of the x vector, x1, x2, t, x2, t. This is vector. And give you the matrix of the corresponding values, and then the x vector again. So this is the normal format you have, and if you take these equations, fill them inappropriate, you'll get 5, 2, -8, and -5. And we usually call this our A matrix, but it can be any letter in general. And something else you want to consider are the initial conditions. So a way to denote that is what x of 0 is. And from here, I did not write down the initial conditions earlier, but they are given to be x1 of 0 is equal to 3, x2 of 0 is equal to 3 as well. So that just means the x vector of 0 will just be 2 3's. Just kind of copying them over. Okay, and then now in terms of the second step, it will be to find the eigenstuff. When I say eigenstuff, I just mean eigenvalues and eigenvectors. And you want to do this because what we're ultimately trying to do is to transform it or do a change of basis into the eigenbasis, like similar to what diagonalization does to simplify our calculations. But we don't know what the eigenbasis is yet, so we need to find the appropriate eigenvalues and eigenvectors to determine this. So we can just take the matrix A and take the determinant of A minus lambda I, so lambda, -8, 5, lambda. And I'm just going to skip through the calculations, but this will basically lead you to lambda is equal to plus or minus 3. And then if you were to solve for the null space accordingly, corresponding to each eigenvalue, you would get the eigenvectors. -1, 1, -1, 4. And this specifically corresponds to -3, and this corresponds to the eigenvalue of 3. So now we have our appropriate eigenvectors, and now you want to do the actual change of coordinates into the eigenbasis, which is going to be step 3. And in order to do this, we come across the same graph that we've been repeatedly talking about, which shows the true importance of this graph. So you have the current basis you're at, and then you have the eigenbasis. You have a transformation here, which is just A. And then this transformation in the corresponding eigenbasis will be the diagonalized matrix. And let's just call this matrix A tilde instead. And same thing, if you have E, which will be the eigenvectors in the matrix, so -1, 1, -1, 4. Then you have V transforms from eigenbasis back to the original basis, and V inverse does the opposite. Cool. And since we know A tilde is supposed to be the diagonal matrix, you can know that this will be the corresponding eigenvalue, so it would be 3, 0, and 0, -3. But a way to confirm without directly using this trait that it is the correct matrix is to consider that what A tilde is equal to. So, similarly to how we solved for A previously, you'd want to mirror those steps to find the appropriate equation for A tilde, which we find out is going to be same thing, let's multiply V inverse A V. So this is definitely something to keep in mind. So cool. So now based on this, we know that if we call these coordinates xe and ye, then we know that, and e as in the coordinates in the eigenbasis, then now we can write that d dt e of t will be equal to a tilde to 3, 0, 0, negative 3 of x. Cool. And we can also rewrite the starting condition, so xe of 0 would be same thing, so but now we're going from the regular basis to the eigenbasis, so you would want to multiply by v inverse 3, 0, 0 inverse and have starting conditions of 3, 3. And if you use the inverse formula, the shortcut for the 2 by 2, you multiply this out and you end up getting negative 5 to the starting condition and the eigenbasis. So now we have our coordinates we have including the initial condition in the eigenbasis already. So the next step is to solve the differential equation, because right now we still have the differential part, the ddt part in our equation. But we want to solve it in this eigenbasis. That's when we go back to using our common eigenbase, our common Diff Eqs, which is basically the exponential. So then, in this case, you know that if you just write the corresponding equation, you know that dt of xe1 of t is equal to 3 xe1 of t, and ddt of d2 of t equal to negative of t. And this corresponds to xe1 of t is equal to e to the dt, because you take this 3, put in the exponent, and you consider the initial condition. So when t is equal to 0, then this entire term would just be 1. So then accordingly, this needs to be the initial condition, which is negative 5. And then you can solve for e2 in a similar way. E2 with the initial condition of 2. So now you have your solutions, but they're in the eigenbasis. So the last step is to convert to original. And how you do this is, now we go back to this graph, is that we're in the eigenbasis right now. You want to convert back to a regular basis. And how you do that is just by multiplying current values by v. So then, based on that, according to our example, we want to get back to x of t, and that's just equal to v of x t of t, which specifically if we write down original v, and then put in our two values, will then be equal to this. And this is just basic matrix vector multiplication. And this is our final answer for what x of t is equal to. Just keep in mind x of t is equal to x of t, so you can get two separate equations appropriately. So we've gone through the basic steps, so the basic 5 steps of solving differential equations, and you can see how this relies basically on the idea of diagonalization, which in suit relies on the idea of change of basis. And you can tell without doing this basis change, your calculations would be much more difficult because you would have to be getting like these a summation of these exponentials. Something I also wanted to point out and to go over is the different types of eigenvalues in terms of how many. So kind of like the idea of no solution versus unique solution versus infinite solutions, which you see in eigenvalues. So this is actually the perfect time to consider an RLC circuit where everything is in. So we have PS, then the resistor, the inductor, and the capacitor. So I'm not going to go over the exact ways of how you write KCL and KVL in order to get the appropriate equations, but you'll basically write the loop rule and then get like the appropriate functions and find eigenvalues for it. So when you find the eigenvalues and you're making the determinant equal to 0 and you multiply the values out, you'll get lambda squared and the is equal to 0. This is what I'm finding eigenvalues. And then in order to solve this for the exact eigenvalues, you will need to take the quadratic formula, which will result in it being negative r over 2l plus or minus r over 2l squared minus l minus l minus 1 over LC. And for simplicity reason, I'm just going to call everything that's in the square root k, so I don't have to repeatedly write it again. So, based on this equation, there's 3 different things that can happen in terms of eigenvalue cases. So, one case is that you can have 2 distinct real eigenvalues. And this specifically happens when k is greater than 0, because then the square root is valid, and since it's not 0, then you're adding a value and then you're subtracting the same value. While the second case that could happen is that you have complex eigenvalues. So we have a plus bi, for example. And this happens when k is less than 0, because then the square root will give you an imaginary number of some sort. And then the last case is that you only have one unique real eigenvalue. And this happens when k is equal to 0, so then the plus and minus doesn't really matter when you have those. So these 3 cases alter your result quite a bit, specifically in what type of function you will get, because as seen in your previous example, what ends up happening is you kind of get a function of the form when you're still in the eigenbasis of, let's see, like k1 e lambda 1 t, right? So this value in the exponent is the lambda, which is the values that we're talking about right now. So if your lambdas are real, so lambdas are real, then your resulting function will be an exponential. while if your lambdas are imaginary, then it would become a sinusoidal based on how sinusoidals are described and presented in exponential form. So this is something to keep in mind, specifically between 1 and 3. The difference is whether you have one exponential term that can be simplified to just one, or two different exponential terms. So yes, so this kind of shows where RLC circuits come into play and why the eigenvalues matter.